is going to change.
Nope. There's actually a really very, very fundamental problem with the size of the box. How do we run these models?
Everything's got to be the same, so you can't have different size boxes depending if you're on the ocean.
Right, now that's two, that is one of the fundamentals. There are two. I've forgotten about this one, yes, you're right. What? Everything's got to be the same size. What's the problem with the Earth? With these boxes?
Spherical.
It's spherical. So as you move up to, so you can have a 200 kilometre by 200 kilometre box down at the equator, but that 200 kilometre box by 200 kilometre box at the North Pole is very, very different because lines of longitude come to, so your actual longitudinal lines, your space and your area changes because you're on a curved surface. And actually trying to solve how you divide up with the meridional effect is a major issue, a major complication, because you, in a sense, although it's three-dimensional, you try to get it down to, especially visualizing it down to two dimensions. So you can see here that these boxes actually, we can say, oh, we'll use 200 by 200 square kilometers, but in reality, if we're using latitude and longitude, they are, let's say we use those as the criteria, the size of the box would change radically as we get towards the North Pole, or the South Pole. But there's still a really fundamental problem about deciding on the size of the box. Let me show you a paper which is one of the ones that, just two or three that I've suggested that you actually read, which is the Edwards History of Climate Modelling in wires. Especially the early part is really quite neat because he starts off going by how these models have developed. So we started way back before Hadley with Edmund Halley, he of the Halley's Comet fame back in 1686. He was interested in trade winds, and Hadley simplified the idea of convection and the equator and convection. Halley did to begin with, and then Hadley came in and simplified his model to introduce Coriolis, and we have a Hadley cell. Very simple idea, okay? Then Ferrell comes along and adds another cell, which is the further complication, so we're making it just a little bit more complicated. And those basic ideas worked, but of course, how did they actually do the calculations? Well, they did the calculations by various types of back-of-the-envelope type calculations. As soon as you get to this sort of modelling structure, you then start getting the issue of how do you calculate it? The first weather model, and I'll just find you the, here we are, Phillips prototype. Right, here we are. First person to attempt a computerized general circulation model in the 1950s used computer power for the first time. Just look at how much he used. In 1955, his mathematical model and memory constraints to the computer were 1 kilobyte of main memory and 2 kilobytes of storage.
Jesus.
Now, now you just imagine trying to run a GCM with 1 kilobyte of memory and 2 kilobytes of storage, and this would be a computer the size of this room, probably, trying to do it. So, in fact, the biggest constraint on your model, this decision of the grid and the box, is, yes, it's the theory, but it's the practical side of how can you compute it? How much power do you need to actually run the model? So you can imagine that every time you add a box, you add a layer in the atmosphere, or you add a layer in the ocean, or you decide to go from 200 kilometre squares to 100 kilometre squares, then you are multiplying up the number of calculations that model has to run. So you can imagine if you suddenly shift your three-dimensional model and you reduce the size of the things by half, then you're increasing the number of calculations by 2 factorial, isn't it? So, you know, huge amount of things. Now, at the moment, for an atmosphere-ocean general circulation model like the Hadley Centre model at Exeter, to do a run for that over, say, 100 years could probably take about 6 months of supercomputer time. But what we've had over time is this, you know, you've seen the graph, I haven't got a copy of it up, of the exponential rise in computer power every decade or whatever. And effectively, when we go back to modelling, what drives the size that you can do it at is not attempting to get close to reality. It's attempting to balance the demands of giving a good approximation of reality against the computer power that's available and cost. Because every time you run a supercomputer, it costs. And if you're tying up a major supercomputer for a month, 2 months or something like that, that's a huge cost in terms of doing it. So the biggest question is, why would you bother to reduce the size of the grid, of the boxes, if the output is only going to improve by 3%, say? You get, this goes back to our question going back right to Arrhenius. If Arrhenius on the back of an envelope can predict CO2 and world global temperature, why do we bother with a supercomputer that costs millions of pounds to come up with the broad answer? Because that's the answer we're interested in. And if we ask what people are now beginning to do with computer models is there's a sort of rather Jeremy Clarkson approach that the bigger it is and the more faster it goes, it must be better. You know, it's the sort of Mach-O equivalent of, look, we can now double our computing power, wow, let's use it, let's run it. And you end up running this model, it costs twice as much, and you end up actually with information that is not that different from what you had before, and is actually the information that you want. So, the question really goes back, what information do we want from a computer model about climate projections? So if you're given the choice, you are your parliamentary candidate for Penryn and Lesser Cornwall, and the question comes up, you know, are you going to vote for doubling the computer? So I'd say to you, right, what do you want from a global computer model? What do you actually want from a global computer model projecting climate change in the future? What are we actually wanting to get from it? So why do we do it? So why do we bother spending all this money and using all this, getting all this information to model into the future? What exactly are we asking from it?
More accurate results so that they can try and prevent.
But what do you mean by accurate?
Or more closer to the truth.
Closer to the truth. Okay, what is the truth? That's a separate question. But closer to the, I mean, what do you want to know? Do you want to know that on Thursday, the 23rd of October 2027, because that's when you're going to get married, you want a sunny day? I mean, is that what you're after, or is it just to say, well, global mean temperature in 2027 will probably be another degree plus or minus 0.1? You know,
it's going to be more useful to have a broad general instead of knowing like one day. You know, like a broad general instead.
but, okay, define broad and general.
Or like if you're saying like pollution, it'd be more important to know temperature than know exact climate on time on one specific day. Like if you've got a year.
We can take that down two ways. You can say, I can say, I can't tell you. Can't even tell you what global temperature. Even if we had this most fantastic model, there's enough noise in the system, I'd still not be able to say in 2027 October what the temperature is likely to be. Give you a probability around it, so it's a probability estimate. But there's this obsession with trying to get to reality of a very complex system. Do we need to always be trying to get nearer and nearer reality?
I think it's also like a governmental thing, because like, in a way, not to scare the people, but in a way to show what reality will be in the future. Like if people don't
So do we need to do that by modelling, or do we need to get broad model ideas and then somehow produce that into a form that people can sort of relate to?
But then
Rather than get a nearer. There's an obsession with regional climate change. I'm not doing it, I do it a bit next year. There's a thing called the UKCP 09, which is basically UKCP 09 is a set of projections of climate based on IPCC syntheses of models. And it goes down to 20 by 20 kilometre, I think it's 20 or 25 kilometre grid squares. So that you can have a map of Cornwall. I was going to put one on, but I thought it might complicate the matter. But effectively, you can predict the likelihood of being warmer, wetter, drier, more extreme across Cornwall. Now, I think that's a load of rubbish in one sense, in that it gives a misleading impression that Boscastle will get warmer, or that Penryn will be warmer than Penzance, which probably will be anyway. But it gives the impression that we can actually say in 2050, this is how much it's going to rain in Penryn. Which is the way the models are. This is what people want to know. This is what my neighbour wants to know about his vines. He wants to know, and I'm not going to say, well, I could write this fantastic model that had its boundary as the southwest, and print out this. I could say, I've just run this for 3 months, and this is the projections for 2025 for South Devon, for this area around here, and yeah, you're spotting the right area. And I know that's absolute claptrap, in the sense that there's so much uncertainty. I could say that for Devon as a whole, the likelihood is that it's going to be this. But it sounds right because it's the idea of truth and the idea of reality, that we are modelling to the point whereby we're actually not modelling. It's not a model anymore. It's actually everything. And as the computer power increases, there's this danger of